All right, welcome back. So I've got a few more minutes here. So what better way what better thing to do than after work video reading the next part of this book. So we're going to move into a pretty mathematically dense section. This will be about regression techniques. Regression is really about predicting an output numeric and continuous value given a set of input variables or features. There are many different algorithms that can be used in this category. Let's review some of them. Linear regression. This is the simplest method of all and still probably one of the most utilized because in life, nature, and many fields, linear relationships are quite common. The formula for this method is as simple as y equals mxb, right? But here's a example of it. So as ports go up, memory is utilized more in a linear fashion. But it should be, y equals mxb plus b. And they're not using m, but instead of using m for the slope, they're using a. So y equals ax plus b, where a equals the slope of the line, an n-dimensional vector. B equals the intercept, and this is a one-dimensional vector. Right. And then y equals the dependent variable, one-dimensional vector, and x equals the independent variable, n-dimensional vector. So y equals mx plus b is something hopefully everyone is familiar with. So the b would be where it intercepts here, so it would be a negative value, not shown on the graph there. The reason why both x and a are n-dimensional vectors is because there could be multiple input variables, x1, x2, x3, all the way up to xn, which together would form an input vector for the linear regression. Contextualized to the ports versus memory example, the formula would be m equals a times p plus b, where m equals device memory, p equals number of ports utilized, a and b are the model parameters we need to find out. So don't let any of this make it more confusing. They're just using different symbols to mean the same thing. It's just the classic y equals mx plus b equation. Hopefully everyone learned in grade school as part of their public education. It's a linear relationship on a graph, and you express that with y equals mx plus b. Y is the axis. X is here, so m and p, so you can swap out y equals mx plus b with m and p, and then normally you would use m to mean the slope for some reason. I don't know why, but here they're using a, and then b where it intercepts with y. So how do we find these parameters and therefore the optimal line? The method is based on computing the least square regression line, LSRL, which is the line that best aligns with the input observations by minimizing the mean square error, MSE. There is, therefore, a cost function that will be represented as the sum of the error for each observation. It depends on the difference between the actual value y and the predicted value y predicted. So I'm going to plug this one into ChatGPT. It's a pretty complex one, so usually it can make it a bit simpler. Just read it out loud at least.
The image you uploaded appears to be a graphical representation of a linear regression analysis, where a line of best fit, red dashed line, is plotted against actual data points, diamond symbols. The x-axis is labeled as the number of ports used, and y-axis is memory utilization accuracy. The equation C equals I equals 1 meter, E minus Y PRED, 2 millicoulombs equals, frac, sum underscore, I equals 1, caret, M, Y underscore I, Y underscore, pret, squared, M, C equals M, and area summation I equals 1 meter, E minus Y PRED, 2 represents the cost function used in linear regression, specifically the mean squared error, MSE. This cost function measures the average squared difference between the observed actual outcomes and the outcomes predicted by the model, helping to determine the best fit line by minimizing the value of CCC.
All right. We have not answered the question above yet. How do we find out the optimal weights, aka model parameters, A and B, that minimize the error C? We are going to introduce here a fundamental mechanism that will apply to many of the supervised learning techniques that will be described. Gradient descent. This is a key tool to iteratively obtain the optimal parameters, aka weights, for the model. In this case, for our linear regression. The goal is to find those weights that will minimize the value of C. C can be represented graphically as a curve based on the different values of weights. In the following diagram, the curve C has been projected based on only one weight, x-axis, but you can imagine a 2D or 3D representation as more weights are included in the model or potentially an n-dimensional representation. So now as the weight goes up and the cost function, so we've got a gradient at this point. So I'm not sure what that means. Let's ask ChatGPT.
The image you've uploaded shows a graph of a cost function CCC plotted against a parameter labeled as weight. The curve represents a typical shape of a cost function in many optimization problems, particularly in machine learning and statistics, such as in gradient descent optimization. The green curve dips down to form a U shape, indicating a quadratic relationship between the cost function and weight. This U-shaped curve is known as a parabola, and the lowest point of the curve represents the minimum cost, which is the optimal value of the weight for the lowest error in model's predictions. The dashed line extending from the curve indicates the gradient, or derivative, of the cost function at that point on the curve. The gradient is a crucial concept in optimization as it points in the direction of a steepest ascent. In the context of optimizing a model, one would typically move against the gradient direction to reach the minimum point efficiently, which in this plot is shown as moving to the left towards the bottom of the curve.
All right, so I didn't catch any of that. I'm just going to keep going. One key characteristic of the curve C, any curve for that matter, is that the derivative is 0 at any minimum or maximum point. The derivative, aka gradient, represents the slope of the curve at a particular point on the curve. If we want to find the weight value that will minimize the cost function, we need to find the one that will correspond to the global minimum of the curve. Let's assume we start our search process at any point in the curve. This is the random parameter initialization we mentioned earlier. The gradient of the curve at that point indicates the speed of increase. We need to move in the direction that takes us to the minimum of the curve. We will apply the iterative process of computing the new weight based on the following formula. So let's get have ChatGPT talk about this.
The image you've uploaded depicts the formula for updating the weight in an optimization algorithm such as gradient descent. Here's how it works. WWW represents the current weight value. Alpha, alpha, alpha is the learning rate, a hyperparameter that determines the size of the steps taken to reach the minimum of the cost function. Partial differential C, partial differential W, frac, partial C, partial W, partial differential W, partial differential C, denotes the gradient of the cost function with respect to the weight WWW. This is the slope of the cost function at the current weight and indicates the direction and rate of steepest increase. WNEWW underscore new W new represents the newly computed weight after an update. The formula W new equals W minus alpha times C partial differential W underscore new equals W alpha times frac partial C partial W new equals W minus alpha times W partial differential C shows that to update weight, use a subtract fraction determined by alpha of the gradient from the current weight. This subtraction is crucial because it means you are moving against the gradient toward the minimum of the cost function. This process is repeated iteratively to minimize the cost function, optimizing the model's parameters.
All right. Intuitively, we are traveling through the C curve in the reverse direction of the gradient at a rate specified by the learning rate parameter. The larger the gradient is, the more steep inclination. The larger the update for W towards a new weight value, that hopefully will be closer to the minimum. Once W is truly at the minimum, the gradient will be 0. Therefore, W will not be changed in subsequent iterations, and the algorithm would have converged to the true minimum of the curve. All right, so we got another gnarly graph there. Let's see what ChatGPT has to say about it.
The image you provided illustrates the iterative process of gradient descent and finding the minimum of a cost function, labeled as CCC, with respect to weight, www. Here's how the depicted process works. W0W_0W0 represents the initial guess for weight. G0G_0G0 is the gradient of the cost function at W0W_0W0. This is the slope of the tangent at that point on the curve, showing the direction of steepest increase. W1 equals W0 minus alpha times G0W_1 equals W_0 alpha times G_0 W1 equals W0 minus alpha times G0. This formula updates weight from W0W_0W0 to W1 W_1 W1 by moving in the direction opposite to the gradient, as indicated by the subtraction. The size of a step taken in this direction is controlled by the learning rate alpha. The process shows W1 W_1 W1 being calculated, and then further updates to W2 W_2 W2 follow the same method. W2 equals W1 minus alpha times G1 W_2 equals W_1 alpha times G_1 W2 equals W1 minus alpha times G1, where G1 G_1 G1 is the gradient at W1 W_1 W1. This iterative update continues, each time recalculating the gradient at the new weight and updating weight accordingly. The graph beautifully illustrates the descent along the curve of the cost function, moving stepwise towards minimum. Each step is guided by the gradient at the current point, and the size of each step is determined by the learning rate alpha. This visual helps in understanding how gradient descent optimizes parameters to minimize errors in predictive models like linear regression or neural networks.
All right, so a few considerations that are important at this stage relative to both linear regression and gradient descent technique. The first consideration is the cost function may have complex forms with multiple local minimums, peaks, and valleys. That means there is never a guarantee that your training process will converge in the global minimum. It may simply converge to a local minimum. Oh yeah, I remember this. I've learned about this before, and this is familiar to me. Both are characterized by a zero gradient. That is why the initialization matters. The two iterations initialized with different values may result in the training converging into different minimums. Due to that, it is convenient to repeat the training process multiple times so that we can statistically discover different minimums and select the one that most likely is the global minimum. So I think I can actually explain this pretty well. So let's say you have your data looks like this. So now as you're going through and doing that, checking the slope through, so you found one here, right? This is where that slope is 0. So you might think, oh, this is the minimum of the whole data, but you haven't checked this one yet. You haven't checked this one yet. And then likewise, if you started here, you might think this is the lowest one, but again, you haven't checked any of these. So what you can do is continually check the data and presumably start in other areas or like do it in different ways, so that if you have data like that, you're checking it enough in enough different ways that you don't just get here and say, oh, this is the minimum stop. Like you've identified more than one minimum, and then you know that the lowest minimum is the actual minimum. Okay, so all right, so that's it for this. So due to that, it's convenient to repeat the training process multiple times so that we can statistically discover different minimums and select the one that most likely is the global minimum. The training process will be highly influenced by the learning rate parameter. This is one of those hyperparameters I have mentioned that will need to be selected. A larger learning rate may accelerate the learning, but may never converge, whereas a small learning rate may increase the chances of convergence to a minimum, but it may take a much longer time. Different values may need to be tested to evaluate what works in each case. There are algorithms that will dynamically adapt this parameter based on the evolution of the training process. So here's another gnarly graph. Let's put it in ChatGPT.
The image you provided demonstrates the effect of a large learning rate, alpha, 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 in the gradient descent optimization process. When the learning rate is too large, it can lead to a behavior known as overshooting, the minimum of the cost function. Here's a breakdown of what is shown. W2, W1, W3, W0, W underscore 2, W underscore 1, W underscore 3, W underscore 0, W2, W1, W3, W0. These labels represent different iterations of the weight as it is updated through the gradient descent algorithm. Overshooting. Instead of gradually converging towards the minimum of the cost function, the updates of weight cause it to bounce back and forth across the minimum. This is due to the updates being too large, which makes it difficult for the algorithm to settle in the lowest point of the cost function. Trajectory of weight updates. The arrows show the trajectory of weight updates. Instead of a steady approach towards the minimum, the weight jumps over the valley from one side to the other. This behavior highlights the importance of choosing an appropriate learning rate for gradient descent. If alpha, alpha, alpha is too large, the algorithm may fail to converge or even diverge, taking larger and more erratic steps around the minimum or away from it. Conversely, a very small alpha, alpha, alpha might lead to slow convergence, wasting computational resources and time. Therefore, tuning the learning rate is crucial for efficient and effective optimization in machine learning models.
All right, looks good to me. So the derivative of C is a function that in the case of a linear regression can be easily obtained. But this is not the case in other more complex models. In those cases, we can take advantage of the support for multiple Python libraries and frameworks that will do that for us. So we do not need to take care of such derivative process. Key takeaway: linear regression, while simple, is very applicable. But most importantly, it is at the heart of all of the more complex machine learning architectures, including neural networks. So you have to understand linear regression really well because it's fundamental to the more advanced stuff. All right, so the next type of regression is polynomial regression. In linear regression, we have assumed a linear relationship between the dependent and independent variables. In many cases, this will not be the case, and we need a more complex curve to estimate the function. Polynomial regression provides more flexibility by including the possibility that the dependent variable is a function of the independent variables raised to the power of n, where n might be 2, 3, 4, and so on. Polynomial regression is a generalization of linear regression. Since a polynomial where n equals 1 is effectively a linear regression. So here we've got polynomial regression, quite a bit different than y equals mx plus b. So we're actually now creating a curve, whereas if we use linear regression, we have a straight line here. Now we can get an even better model here by using polynomial regression. Let's see what ChatGPT has to say about that.
The image you've uploaded illustrates a polynomial regression model, where a curved line is fitted to a set of data points that represent memory utilization in millivolts, MB, as a function of the number of ports used. Here's a breakdown of the elements in the graph. Data points, represented by diamonds. These points are the observed values of memory utilization for different numbers of ports used. Polynomial regression curve. This is the curve y equals b0 plus b1 times x plus b2 times x2 plus b3 times x3 plus bn times x and y equals b underscore o plus b underscore 1 times x plus b underscore 2 times x squared plus b underscore 3 times x cubed plus dots plus b underscore n times x squared and y equals b0 plus b1 times x plus b2 times x2 plus b3 times x3 plus bn times x n shown in the graph. Is a polynomial of degree n and n, where b0, b1, bn b underscore 0, b underscore 1, dots, b underscore n b0, b1, bn are the coefficients that have been determined to fit the curve as closely as possible to the data points. X-axis, hash of ports used, p equals x. This axis represents the independent variable, which is the number of ports used. Y-axis, memory utilization, MB. This axis represents the dependent variable, which is memory utilization measured in millivolts. The polynomial model is more flexible than a linear model, allowing it to fit a wider range of data shapes. The degree of the polynomial NN determines the curve's flexibility. As the degree increases, the polynomial can fit more complex data patterns, but there's also a high risk of overfitting, where the model fits the noise in the data rather than the underlying trend. This model appears to be capturing a nonlinear trend in the dataset, suggesting that as the number of ports increases, memory utilization increases nonlinearly.
All right, so that was good. So we can estimate curves as opposed to straight lines to approximate our regression function using polynomial regression. The risk with polynomial regression, as with any more powerful model, is the possibility of overfitting, as was mentioned in ChatGPT. Polynomial regression tends to be very good at fitting within the range of the values we have samples for, but then outside that range tends to deviate significantly. A polynomial like the following seems to align very well with the observations provided. However, outside that range, it deviates even to the point of producing negative values, which makes no sense in our target dependent variable memory utilization. You can't have negative memory utilization. So it's just a model. It doesn't know what it actually is doing, so it can give you results that you don't want. All right, ChatGPT is left speechless by this. It absolutely cannot think of a single thing to say about this graph. So,
The graph we've uploaded shows a more complex relationship between the number of ports used and memory utilization, depicted as a series of peaks and troughs. The curve fitted through the data points, represented by diamonds, suggests that a higher order polynomial regression or possibly another type of nonlinear model have been used to capture the underlying trend. Here's a breakdown. Peaks and troughs. The presence of multiple peaks and troughs in the curve indicates that memory utilization responds to changes in the number of ports in a nonlinear and non-monotonic manner. This can be due to underlying complexities in how resources are managed or allocated as the number of ports changes. Data points. The diamond symbols represent observed values of memory utilization for various numbers of ports used. Fit curve. This curve likely represents a higher order polynomial given its ability to model the observed fluctuations. The exact degree of the polynomial isn't specified but would need to be sufficiently high to accommodate all the visible turns in the trend. This kind of detailed modeling is essential when the relationship between variables is complex and not well approximated by simple linear or low-degree polynomial regressions. However, care must be taken to avoid overfitting, especially with limited data points, as a model too closely fitted to the existing data might not perform well on new, unseen data. This graph is an excellent illustration of the challenges and considerations in statistical modeling and machine learning for real-world applications where data behavior is intricate.
oh, good. So, high praise from ChatGPT. Therefore, as with any model that has flexibility, we need to be careful in controlling the complexity of the model in order not to overfit. From the algorithm's implementation perspective, the polynomial regression training process is precisely the same as the linear regression. Ultimately, as you can see, a linear regression, which we estimate after having transformed the input variable x. Let's remember, x may be a vector of multiple variables, all the way up through, I think this is a typo here. I think it's meant to be n, but it's not a typo I'm going to send to the author because I feel like the meaning is preserved. And in fact, it might even not be a typo because it might be talking about memory. So this might be as it goes on to memory, but regardless of if it's a typo or not, I feel like it doesn't, like before when it was a / rather than a pipe key, that introduced in my mind the concept of division to this mathematical concept where the concept of division did not belong. So that I definitely had to go and submit the correction for that. But for this, I'm just going to move on. And I don't even know for sure if this is a typo. In the prior one I talked about, it is a typo to have a / in that sort of probability notation. In a new set of variables, Okay, so let's remember x may be a vector of multiple variables in a new set of variables. Similar, yeah. Now n's used, and now they're exponents. Nevertheless, once we have generated such new variables, the regression itself is linear with respect to such new variables, not with respect to x, though. This is an excellent time to introduce a new concept that we have implicitly seen here in the polynomial regression. Even if your input variable is x, you may use transformations of x to build and train your model. Polynomial regression generates new variables, features, by raising to a specific power. However, to train your model, it may be relevant to compute the rate or derivative of your metric, compute the logarithm of it, or the square root, or compute the ratio between two existing variables, etc. There are many possibilities to determine the genuinely relevant features you must use to build and train your model out of the raw features you have available as a starting point. There is a process of feature creation or feature selection. How do you determine which feature you should create? Your domain expertise, your intuition will be required to identify them. Very frequently, it may not be obvious what you need to do or what would be the truly significant feature that helps build a successful model. As we will see later on in the book with neural networks, this process of feature selection or feature creation happens automatically. All right, so we've got a graphic here. So this is feature transformation and selection. Let's see what ChatGPT has to say about it. Maybe it'll have some high praise again.
The diagram you've uploaded outlines a typical process in machine learning related to feature transformation and selection, leading into an ML model that outputs a prediction YYY. Here's a breakdown of each component in the diagram. Feature inputs x1, x2, xn, x_1, x_2, x_n, x1, x2, xn. These are the original features or inputs into the model, which can be variables like age, income, number of products purchased, etc., depending on the specific application. Feature transformation and selection, PCA, principal component analysis. This is used for dimensionality reduction, transforming possibly correlated features into a number of uncorrelated variables called principal components. Scaling, adjust the range of the data, e.g., normalization or standardization, to ensure that no variable dominates the model due to its scale. Normalization, similar to scaling, involves adjusting data measurements so they are on a comparable scale, typically a 0 to 1 range. Rate, derivative, ratios, power, log. These transformations can help linearize relationships between features and the outcome or highlight trends that are not apparent in the raw data. Transform features, Z1, Z2, ZM, Z_1, Z_2, Z_M, Z1, Z2, ZM. These are the new features generated from the original set XXX for various transformations, selected for their potential to improve the performance of the ML model. ML model. This is a machine learning algorithm that takes the transformed features Z's as input and produces an output YYY. The specific type of ML model could range from simple linear regression to more complex models like neural networks or ensemble methods. Output YYY. The final prediction or output of the model. This could be a class label and classification problems, e.g., spam or not spam, a continuous value in regression problems, e.g., predicting house prices, or any other type of output depending on the problem being solved. This diagram captures the essence of many machine learning workflows, emphasizing the importance of preprocessing steps to ensure the data fed into the model is the most informative and structured in a way that maximizes the model's ability to learn and make accurate predictions.
Okay, so I think next time I do this, I'm going to prompt it a bit differently because it says like why, because it's using a special format here and having trouble reading that out. So I'll make sure to do that next time I plug something into ChatGPT. But for now, this section has a key takeaway. Feature selection or feature engineering is one of the most important, if not the most important, task of the entire process. It is really about determining what information is the truly relevant for our machine learning model. And the author is from Spain, so there's a little bit of editing things, but more or less the meaning is there. Nevertheless, for now, for methods like linear regression and some of the following ones we will describe next, there is a manual decision on which features must be created to better build and train our model. All right, so this next part is about decision trees, and I think I'm out of time. I just had time for a short one, so stay tuned for the next video about decision trees.